Hello everyone, my name is Dionysios Sourailidis. I am a doctoral candidate at the Laboratory of Nonlinear Systems, Circuit and Complexity, LANSCOM, from Aristotle University of Thessaloniki in Greece. And today I will present our work in Antimonotonicity, Crisis and Route to Chaos in the Tumour Growth Model. So the outline of this presentation is as follows. First, we will say a few words about chaos and its relation to cancer. Then we will mathematically model a tumorous growth. After that, we will discuss the results we see. And finally, we will talk about ideas for future work. So what is chaos? Chaotic systems are deterministic systems with extreme sensitivity to initial conditions and parameter values, which means that systems with almost identical initial conditions values will give completely different solution trajectories. As you can see here, the double pendulum below. So where is chaos found? Chaos is found almost everywhere in nature, namely engineering, biology, astronomy, economy, and many more. Chaos has numerous applications, such as text, image, sound encryption, and secure communications, robotics, and many more. Now, what about cancer? Cancer is a blanket name, which is assigned to a complex network of interactions of malignant cells, which no longer possess specialization and control over normal growth. This network of malignant cells could be treated as a nonlinear dynamical system, self-organized in time and space, definitely not in thermodynamic equilibrium, indicating high complexity, robustness, and versatility. The concept of modeling cancerous growth using dynamical systems was first proposed by Carol Newton in 1980. Many researchers caught on and proposed newer and more precise models as years passed. In the present work, we study an intriguing model that was recently proposed by LANOS, PEREZ et al. So what about this system? The LANOS PEREZ model, which was proposed in 2016, is based on a chemical network and describes the mechanism for a vascular, and metastasis tumor growth. As you can see in the system of equations below. In this system, the variables x, y, z represent the proliferating tumor cells in the avascular, vascular, and metastasis phases, respectively. Also, parameter n represents the population of normal cells, eta is the population of the host cells, and I is the population of immune cells, which are the T lymphocytes as well as the natural killer cells. In the present work, we conducted dynamical analysis of this system. Namely, the system is integrated numerically using the classical fourth-order Runge-Kutta integration algorithm. For each set of parameters used in this work, the time step is always 10 to the power of minus 3, and the calculations are performed using variables and parameters in extended precision mode. For each parameter settings, the system is integrated for a sufficiently long time and the transient is discarded. Furthermore, Lyapunov exponents of the system for the chosen set of parameters and initial conditions are calculated each time by using the Wolf et al. Algorithm. So, as you can see here in this chart, the bifurcation diagram, for the lower values of the parameter eta, we observe that the system retains a periodic behavior for all values of the bifurcation parameter n. This can be seen, for example, in this figure, where for eta equals 2, the system is periodic with period 1. As the parameter eta, though, increases, the phenomenon of antomonotonicity appears, as can be seen in figure B. For eta equals 3.5, in C for eta equals 4.2, and in D for eta equals 4.3. In all these cases, the system starts from period 1, and then the period begins to double for values of n around n equals 3.5, going up to period 2, period 4 for eta equals 4.2, and period 8 for eta equals to 4.3, after which the period is halved back to 1. This is signified by the characteristic formation of a bubble shape in the bifurcation diagram. Interestingly, for larger value of eta, for example, eta equals 4.5, the phenomenon of antimonotonicity extends to chaotic behavior, as can be seen in this figure. Here, the system starts from period 1 and traverses to chaotic behavior through a period doubling route, only to go back again to period 1 following a reverse period halving route. As the value of eta increases even more, the chaotic behavior of the system becomes much more complex. Taking a look at the bifurcation diagram shown in this slide, a plethora of chaotic bubbles are observed. Also, the system repeatedly abruptly exits or enters chaos, as can be seen from the crisp changes in the shape of the bifurcation diagram. This phenomenon is known as crisis. Also, it can be observed that the chaotic behavior appears for a much wider range of the parameter n than before. This figure shows us an example of the system's 3D chaotic attractor. This is the face portrait using those initial conditions. And this is also an example of a diagram of two largest Lyapunov exponents for eta equals 12 here, which verifies the chaotic nature of the system. Finally, the emergence of coexisting attractors of the system is studied by computing its continuation diagram. This diagram is similar to the bifurcation diagram, with the only difference being that each time the bifurcation parameter is iterated, the initial condition of the system is taken as equal to the final state of the system from the previous simulation. Hence, in each iteration, the initial condition of the system changes, as opposed to the bifurcation diagram where it is kept steady. This is done in order to unmask any possible changes in the dynamical behavior of the system with respect to initial conditions. Indeed, as can be seen from the overlapping of the bifurcation and continuation diagrams shown in this slide, the system showcases coexisting attractors roughly from n equals to 376 to n equals to 387 around here. And this indicates that the initial conditions can greatly affect the behavior of the system for this range of parameter values. And in this slide, you can see the phase portraits of the system's coexisting attractors for n equals to 3.778, eta equals 8, and I equals 1, with those in the initial conditions. As the value of the host cell's eta increases, the behavior of the system becomes more complex and unpredictable, since periodic and chaotic behaviors alternate with each other abruptly, as the value of the normal cell's n increases. This observation further underlines our knowledge on the complexity of the tumor dynamics and the need of robust control strategies to keep its dynamics stable around the desired level. Overall, it is clear that even this simplified cancer model can showcase a very complex behavior, which further underlines the complexity of the disease and the difficulties in understanding the full spectrum of cancer dynamics in the body. Future aspects of this work will consider the design of control strategies and also modifications of the system, where control parameter, like the number of immune cells, can be periodically perturbed in order to study the effects of periodic treatment and drug regulation. Also, fractional order versions of this model can be considered as well. This is it. This has been my presentation. Thank you very much for your attention.